Welcome to the course on microprocessor and microcontroller. So, the module 1 I will be discussing about the history of 8086 family and the architecture pin configuration of 8086 and 8088 microprocessor. So, to start with, Intel brought out the first 4-bit microprocessor in the year 1971, and this particular processor had only 2300 transistors working at about 400 to 800 kilohertz. It is a 4-bit microprocessor, that means that the word size was only 4 bits. It was packed in 16-pin DIP package. Following it, the next processor was 8008, which was an 8-bit processor. Since the 8-bit processor which was brought to the market as 8008 was not very much helpful, it was further improved by Intel to bring out 8085 or 8080 microprocessor followed by 8085 microprocessor. So, the 8080 microprocessor came to the market in the year 1974 and 8085 in 1976. There is a small difference between these two, and 8085 is a much better processor because it had incorporated the timing and control within the processor, whereas 8080 processor 8-bit processor had external timing control system. So, 8080 microprocessor had 4500 transistors as against 8085 which had 6500 transistors. It is made up of NMOS technology and had a range from 5 to 10 megahertz, and it is an 8-bit size. That means that it used to interact with the external with 8-bit data bus. So, it was possible to read 8-bit data as well as write 8-bit data into this particular processor. It was packed in 40-pin dual-in package. There is a small difference between 8080 and 8085 with respect to the instruction set. The number of instructions available on 8080 is 111 as against 8085 113. The two different instructions are SIM and RIM instruction. Since we are not interested in 8085 or 8080 microprocessor, let us go to the next point, saying that these processors had an memory of 64K, and it had 16 address lines which could address these 64 address lines and 8 data lines to the external world. This was the processor in which the microcode ROM was embedded to make the processor work satisfactorily. Let us come to the next processor, which is 8086 and 8088 microprocessor, to which we will be going in detail in this particular course. It was brought, 8086 was brought in 1978, whereas 8088 was brought in 1979, and this particular processor had 3 micrometer processors with NMOS technology having 29,000 transistors. It used to work at the speed of 5 to 10 megahertz. They had 133 instructions. There are 16-bit word size. It means that internally the bus was 16 bits to which the data could be operated on. They are packed on 40-pin dual-in package. The total memory that it could access to the external world is 1 megabytes physical memory. These processors too had microcode ROM in it. There has been a huge difference between 8086 and 8085 8-bit and 16-bit processor. Let us briefly look into some of them which makes it clear. Address lines, 8085 16, as a result of 16 address lines you can access 2 to the power of 16 locations. So, that means that it could access 64 kilobytes of memory. Unlike 8086, which had 20 address lines, could access 2 to the power of 20 address locations. That means it could access 1 megabytes of memory. The data that could be accessed as 8 bits in 8085 as against 8086 we had 16-bit data lines. 8085 did not have any coprocessor. A coprocessor is a special type of a chip which has all the arithmetic operations that could be operated upon, whereas 8086 had this coprocessor which was brought out and could be connected with along with 8086 to make it much more powerful. 8085 did not have a very rugged operating system, but the first operating system which was brought into the microprocessor world was CP bar M processor, and 8086 had DOS processor. CP bar M originally standing for control program monitor, and later control program for microcomputers was being used, is a mass market operating system created for Intel 8080 and 8085 based microprocessor by Gray Kendall of Digital Research Insurance. Now there is a huge difference between 8086 and 8088 which we will go through in detail as we go through the course, but to start with, let us know the basic difference between these two. When you are trying to talk about 8086 and 8088, which was brought 1 year later, we have total number of address lines for both to be equal to 20, and hence it was possible for us to really access in case of 8088 and 8086 1 megabyte. The data lines that is available for 8086 is only 8 bits as against 8086 which is 16 bit data lines are being available. So there is an operating system for 8088 which is the disk operating system, but 8086 microprocessor had a different type of operating system, and to start with, to make all the peripheral chips that was available in the market which was 8 bit, this 8088 microprocessor was brought into the market. Let us look into the other improvement that has taken place when you are trying to talk about the Intel family. 80286. 80286 was brought in the year 1982 having virtual memory. It has an improvement with respect to the size of the processor, which is 1.5 micron meters, which is made up of NMOS technology. This has 134K transistors working at a speed of 10 to 16 megahertz. It has 16 bit word size. So that means that 8086 and 80286 both have 16 bit word size to really access from the external world. We have a physical memory of 16 megabytes of physical memory. It is put in a 68 pin PGA. PGA stands for pin grid array. It has bit slice clearly visible. Now looking into the difference between the 8086 and 8086, 8086 has only 20 address lines as against 80286 which has got 24 address lines. The number of pins is 40 in case of 8086, whereas 80286 has got 68 pins. The virtual memory that is available in 80286 which is of 1 gigabyte as against 8086 does not have any virtual memory. Talking about the physical memory which it can really access, we have 1 megabyte of physical memory in case of 8086 as against 16 megabytes in 80286. 80286 can be operated on a protective mode which has 16 MB of memory as against 8086 which does not have any protective mechanism. Now let us look into 80386. 80386 is a 32-bit processor which was brought to the market in the year 1985, which is made up of CMOS technology having 1.5 to 1 micron meter, and 276K transistors are being embedded into it. It works at the speed of 16 to 33 megahertz. It is 32-bit word size, 132 pin GPA, 32 address lines, so 32-bit data paths and 16 terabytes of virtual memory, and it has synchronized control operation of interacting with the external world. The next processor which has been brought out is 80486 by Intel, which has a pipelining which is brought in the year 1989, CMOS technology, having a floating point unit, 8 kilobyte of cache, 168 pin and 1 to 0.6 micrometer process and 1.2 million transistors. It works at a speed of 25 to 33 megahertz. It has 32-bit word size and it is housed in 168 pin PGA. It has a virtual memory of 64 terabytes. So, it has a cache, integer data paths, floating point unit, microcode is being used to make it work and has synchronized control. Having looked into these processors where there has been a continuous change in the speed of operation as well as the size of the transistors have been reduced, it has been possible to incorporate an higher speed system which is required for the external world. To make this speed much more faster which is required by the market, the data paths have also been increased in all these processors which has been mentioned till now. To make it much more stronger, the more processors have been brought out by Intel. One of them is Pentium processor, which is a super scalar which was brought in the year 1993. In this particular type of processor, it works 2 instructions per cycle and it has an 8 kilobyte of cache, one for instruction, another 8 kilobyte for data. So, as we are trying to look at this, look into the other important features that are available for Pentium processor. We have 0.8 to 0.35 micrometer process, 3.2 million transistors have been embedded. It works at 60 to 300 megahertz, 32-bit word size, 296 PGA chip. It has 4 gigabytes of physical memory, 64 terabytes of virtual memory. It has cache, data path, floating point units, control. Now, looking into these, we directly say that there have been quite a huge improvement that is being taking place in the microprocessor world. The dynamic execution in the year 1995 to 1991 was brought out by Pentium Pro, Pentium Pro 2 and 3, which had 3 micro ops per cycle. Out of order execution. When I say it is an out of order execution, the program whatever is being given by the user, this instruction will not be executed in the same sequence, there may be a small change. So, the order is being changed and so it is called as an out of order execution. This we will discuss if time permits to know about the further improvement in the processor in days to come. So, this particular Pentium processor has got 16 to 32 kilobytes of cache for instruction and data. Multimedia instructions were also being provided for the household applications and for games. Games have become quite vital in today's world. Students, children, parents, even the public would really want to use multimedia to large extent. Hence, this had to be included to make it much more popular. So, multimedia instructions were incorporated in the chip to make it work much faster. Pentium 3 adds 256 plus kilobytes of L2 cache. When you say L2 cache, it means that there are hierarchy of memory. When I say hierarchy, there are different levels of memory. We are trying to talk about L1 cache is very close to the CPU, L2 cache is slightly above it, and so we mention it as L2 cache. This is being used to enhance the speed of operation of the processor. We have 0.6 to 0.18 mm micrometer processors, and we have 5.5 million to 28 million transistors, which is working at 166 to 1 gigahertz, and it has a 32-bit bit processor, where we try to look at the overall operation of Pentium processor to be much faster. We have the next version which came in the year 2001 called Pentium 4, which works on deep pipeline. We will discuss about the pipeline starting from 8086 processor in the coming slides. For the time being, let us go through the improvement whatever has happened with respect to x86 processor, and this Pentium processor has a very fast clock, having a cache of 256 to 1 megabyte L2 cache. The characteristics are, it has got 180 to 90 nanometer processing, 42 to 125 mega transistors, 1.4 to 3.4 gigahertz, 32-bit word size, 478 pin PGA. Unit starts to become invisible on this particular scale. Now, as it is being said, have been discussing about the different processors starting from 4-bit with respect to 4004 to now 32-bit processor having as many as 34 data transfer possible. Now, let us look into in detail in each one of them, trying to say how is a processor defined as an 8-bit processor, 16-bit processor, 32-bit processor, etc. We define a processor to be an 8-bit processor if it has 8-bit data lines, internal bus is of 8 bits and its operation is also 8 bits. So, arithmetic logic unit will work for 8 bits. Similarly, when I say a processor is 16 bits, we say the internal bus is of 16 bits and we have an arithmetic logic unit which works as 16 bits, we have external access as 16 bits. So, 8086 is a 16-bit processor, it has got 16 data lines, all internal registers are 16 bits long. I add one more point here saying that internal arithmetic logic unit operation operates on 16-bit data. But there is a small difference when you are trying to talk about 8088 microprocessor. Since we are now discussing in this particular course 8086 as well as 8088, it is my important point to really mention that 8088 has an 8-bit data lines, but internally it has got 16-bit long internal registers and internal bus. So, is 8088 a 16-bit processor or an 8-bit processor? When you are trying to talk about the processing capability of 8088, since it can process 16-bit of data, we call this one a 16-bit processor, but to make it convenient externally we have 8 bits data line which is being connected, and hence we have 8088 data bus to be on the 8 bits and internally it has got 16 bits for its all operation. Similarly, when you are trying to talk about a 30-bit processor, all internal registers are 32 bits long and it has 32-bit data bus internally. The arithmetic operation is also 32 bits. Now, let us look into the internal architecture of 8086 and 8088 microprocessor. Now, the way in which we try to look into this particular processor is to understand the complete operation. Once you know the operation of 8086 and 8088 microprocessor and know some basics about the pin configuration, you would be able to really understand how an instruction executes and how the system works altogether. So, it becomes convenient for you to do the programming. So, when you look at 8086 internal architecture, it is divided into two units. One unit is the execution unit, the other one is the bus interface unit. The execution unit and bus interface unit both work independently, they do not depend upon each other. The bus interface unit basically consists of 3 blocks. One is instruction queue, second one is instruction pointer, and we have segment register. We will discuss each one of them as we go further. For the time being, I am just trying to mention that what you have an in the bus interface unit. So, bus interface unit consists of instruction queue, instruction pointer, segment register. The execution unit is the unit where the actual operation takes place. It has got general purpose register, arithmetic logic unit and flag register. So, the flag register is related to the arithmetic logic unit because whatever operation takes place in arithmetic logic unit, that is being projected to the flag register. Now, the data has to be obtained from some register, and this particular data, whatever is required for the arithmetic or logical operation, is obtained from the general purpose register. So, we are trying to talk about these two units, the bus interface unit and the execution unit, in greater detail as we go further. So, the internal architecture of 8086 is basically divided into two parts. One part is the bus interface unit, which is connected to the external world. The other one is the execution unit. This unit consists of all the registers which is required for the required operation for execution within the system. Now, let us look into the further part with respect to the architecture. It becomes convenient to write the architecture dividing the two parts by a single line, which we call as an internal bus. So, the internal bus, one side we have the bus interface unit, the other side we have the execution unit. We have the segment registers and an instruction pointer, this is another block, and we have a queue, and we have the address calculation and bus control. These are the points which you have in the bus interface unit. In the execution unit, we have the general purpose register, we have arithmetic logic unit and the flags related. So, I am just giving you a block here, and we will be talking about each one of them in greater detail as we go further. So, the whole operation of the 8086 microprocessor is being controlled by the control unit, which is shown by a block which is connected between the bus interface unit and execution unit. So, this particular unit is the one which makes the complete operation of 8086 microprocessor. Let me start off trying to talk about how the system works. How do you say that the bus interface unit and execution unit are independent? Whenever the data is being or instruction is brought from the external world, that is loaded into the queue. The bus interface unit brings 2 bytes of data at one stroke and puts it into the queue. As long as the queue has 2 bytes free, the bus interface unit does not fetch any data. Once it fetches the, if I say data, in this particular case we are trying to talk about the operational code, a code which is of 16 bits is brought and loaded into the queue. And once the bus interface unit fetches this particular code and puts it in the queue, the control unit accesses this particular data from the queue and starts executing the program. Till then the execution unit is idle, and as soon as the execution starts using this particular operation, the bus interface unit is free to fetch the next 2 bytes of the code and puts it into the queue, and the execution unit does the operation independently in respect to the bus interface unit. If the execution unit requires some data and that data is available in the memory, then it requests the bus interface unit to fetch the data for its operation in the execution unit. That is the time when the execution unit has to wait for the bus interface unit to fetch the data. As soon as the execution unit gives this information to the bus interface unit, the bus interface unit will complete its present cycle of fetching the data and putting it into the queue. Afterwards, it executes the required instruction that is being provided by the execution unit and fetches the required data and puts it to the execution unit for its operation. So, when you are trying to talk about this operation, the execution unit and bus interface unit being operated independently, it is possible that both can work together, as a result of which the speed of operation is much faster. This type of a bus division was not available in the lower version of x86 like 8085 or 8080 processor. This is the first time which was brought by Intel to make these two units independently. Now let us look into the internal architecture with greater detail. So as I have mentioned earlier, we have a line separating the bus interface unit and execution unit, and let us go to the next one, which is trying to talk about what exactly does this bus interface unit and execution unit does. So the bus interface unit and execution unit operate asynchronously. So that means that they can operate independently. The execution unit waits for the instruction object code to be fetched from the memory by the bus interface unit. So that means that as soon as you switch on the system and the system starts operating, the bus interface unit executes the instruction, fetches the code and puts it into the queue of the bus interface unit. From the queue, the control unit takes the information and gives to the execution units to start doing the operation. When this code is being brought into the execution unit starts working. The bus interface unit fetches or prefetches the object code 16 bits at a time and loads it into the 6-byte queue. Execution unit fetches the instruction object code from the front of the instruction queue and executes the instruction sequence specified by the clock cycle, because there are some instructions which takes more number of clock periods. When the queue is empty, 2 bytes empty, only then the bus interface unit fetches it and puts it into the queue. The bus interface unit is independent of the execution unit and attempts to keep the 6 bytes queue filled with the instruction object queue. If 2 or more of these 6 bytes are empty, then the bus interface unit executes the instruction fetch mission cycle as long as the execution unit does not have an active request for the bus access pending. Now let us look at one important point here. When you are trying to talk about the bus interface unit and execution unit being operated asynchronously, what happens if there is an instruction such as jump? Non-sequential instructions are being executed. Automatically the control units clears the queue and fetches the instruction fresh and loads it into the queue. So this is a major point which all of us have to understand, trying to say that this particular operation of bus interface unit and execution unit being operated independently enables it to perform operation much better. Now let us look into the execution unit modules. First one is we will talk about the register section. In the register section we have basically few registers like AX, BX, CX and DX. These 4 registers are called as general purpose register, which are of 16 bits. These are further divided into 8-bit registers as AL and AH register, BL and BH register, CL and CH register, DL and DH register. Then we have source index SI register, DI as destination index register, BP as base pointer, SP as stack pointer. Now let us go to the next one where we will be discussing in greater detail about these registers, because we need to know about these registers, because we will be using this register for all the programming aspect of it. As I have already mentioned, in case of a general purpose register, we call this as general purpose register because they have specific operation to be performed, but this can store any 8-bit data or 16-bit data based on the type of registers that is being considered. If you are trying to talk about any 8 bits, it can be in AL, AH, BL, BH, CL, CH, DL or CH, DH. That means that totally we have 8 8-bit registers where the data can be stored. But when you are trying to talk about considering the 16-bit data to be used, obviously we need to have a specific set of registers like AL and H combined together, we can have a 16-bit register. Similarly, BL and BH can be combined to form a 16-bit register. CL and CH combined to form a 16-bit CX register. Similarly, DL and DH combined together forms a 16-bit register. One thing you will have to understand, saying that these registers have specific application when you are trying to do the program. Let us look at them. What are the special features of each of these registers? Let us talk about AX register, which is a 16-bit register. A 16-bit register can be used for word multiplication, word division and word IO operation. What do you mean by that? It means that whenever you are performing a 16-bit multiplication, one of the operand of the multiplication has to be in AX register. Similarly, when you are trying to talk about performing a division operation, so the division operation that can be performed are 16-bit by 8-bit division or 32-bit by 8-bit 16-bit division. So, when you are trying to say that you want to perform a 32-bit by 16-bit division, the lower order 16-bit of data is available in AX register. What about the other higher order 16-bit? The higher order 16-bit is available in DX register. So, DX and AX register are combined together to form an 32-bit register, so that 32-bit data divided by 16-bit register, any other register or memory location could be used for division. Now, let us look at what is this IO operation. Whenever you want to transfer the data from the microprocessor to an IO device externally, or whenever you want to read the data externally into the microprocessor, the data always comes through AX register. When it comes into AX register. When it sends out of AX register. It means that a 16-bit data that is coming from an IO device, it has to be from only AX register. So, IO access is possible only through AX register. Next, let us look at EAL register, which is an 8-bit of the 16-bit register. Apart from when you are not using the AX register for any of this operation, AL register can be used for byte multiplication, byte division, byte IO, translate and decimal arithmetic. Let me briefly talk about it, because we will be discussing in greater detail when you are trying to talk about the instruction set, how these operations are being held. But for the time being, we need to understand that what is the purpose of AL register, what is the special feature of AL register. Hence, I have tried to consolidate and give at one point the advantage of using AL register, or the way in which you can use the AL register. One, AL register is used for byte multiplication. What do you mean by that? When you have an 8-bit by 8-bit multiplication, one of the operand has to be in AL register. The other operand can be either in another register or it can be in memory location. When you are trying to talk about byte division, when you say 16-bit by 8 division, obviously when you are performing the operation of 16-bit, AX has the 16-bit of data, the lower divider can be from any location, memory location or register, but the result whatever you get is stored in AL register. So, as we are trying to talk about a division operation, you will know in greater detail the way in which the operation takes place. But in general, whenever you are trying to talk about AL register, we directly say that the result of a 16-bit operation, result of division of a 16-bit operation by 8-bit operation, the results, that is the quotient, is available in AL register. Now, trying to talk about an IO operation. When you talk about IO operation, we try to say that the way in which you transfer an 8-bit of data to the external world. Maybe it can be from a keyboard, or it can be from a 7-segment display, or it can be for an LED. When you are sending the data out of the microprocessor, the 8-bit of data has to be available in AL register. Now, translate is a special type of instruction which you have in 8086, where we use AL register to convert one code to another. We use the instruction SXLAT. Anyway, I am not interested in discussing now the complete instruction set, but I am going to give this information that enables you to understand the importance of AL register. The other operations that is possible using AL register are all decimal operation. we have decimal adjust after addition, decimal adjust after subtraction. So, we have such an instruction where it is possible to perform decimal operation, BCD addition and BCD subtraction, BCD multiplication. Similarly, ASCII addition, ASCII subtraction, all these operations use AL register. So, AL register has got a special feature when you are trying to talk about all the operations. Looking into AH register has got a byte multiplication as well as byte division. So, when you are multiplying 8 bit by 8 bit, the result whatever you get will be 16 bit. So, 8 bit of multiplication which is available in AL register is multiplied with some other data, the result whatever you get, the lower order 8 bit will be available in AL register, the higher order 8 bit will be available in AH register. So, having said this, similarly when you are trying to talk about division of 16 bit by 8 bits, 16 bit of data when it is divided, AX divided by any 8 bit data, immediate data or contents of a particular memory location or any other register, we get the quotient and remainder. The quotient is available in AL register and AH contains the remainder. So, you understand that the importance of trying to use these three registers, which is quite important. One important point to note is whenever we are trying to talk about AX register and AL or AH register, we say that AX register is also called as an accumulator. So, many times it so happens that instead of calling it as AX 16 bit AX register, we say 16 bit accumulator. Similarly, if you are trying to talk about an 8 bit accumulator, we say AL as an accumulator because it has so much of importance in 8086 microprocessor that it is being used extensively and hence it is being called as accumulator. Similarly, we have BX register, which is a special register which is used for base register. Base register is a special register which is being used to have the address of a particular memory location, and when you are using a translate instruction, the address of the code is available in BX register. The further details of these two will be understood when instructions are being discussed, but to know the importance of BX register, I have just mentioned again, BX register is used for base register and also for translation. CX register is a special register used for string operation, which will have a CX register will have a counter where the value in the CX register can be 0000 to FFFF when you are putting it in hexa. So, that means that we can have 64K count available putting into CX register. So, all the string operations makes use of this particular register as a special register as a counter. CL register is again an 8 bit register of CX which has a special operation for shift operation and rotate operation. Both shift and rotate operation can be performed by using CL register because CL register can have a count of 8 bits. So, this value is being used for rotate or shift operation. Usually the number of bits that is available for 8 bit rotation or a 16 bit rotation is limited to 8 or 16, and hence CL register can contain 4 or 8 or 16 so that it can be rotated or shifted as required. As already mentioned, DX register is used for word multiplication, word division and for indirect IO operation. So, when I am trying to talk about IO operation, IO operation is trying to access the data from the external world. So, let me once again reiterate the word multiplication, word division and indirect IO. Word multiplication is nothing but 16 by 16 bit multiplication. One of the operand, that is 16 bit data, is available in AX register. Another may be available in either some other register or in memory location. After the multiplication, the result whatever you get is 32 bits, lower order 16 bits available in AX register, the remaining 16 bits is available in DX register for multiplication. Similarly, when you are performing a 32 bit division by 16 bit division, higher order 16 bit of data is loaded into DX register and lower order 16 bit is loaded into AX register. Combined together it becomes a 32 bit register. Performing a division by 16 bit, the quotient is stored in AX register, remainder is stored in DX register. The last, which is quite important, is indirect IO. Whenever you are trying to access an external world data, you require to identify the external device by an address. This address can be stored in DX register. So, DX register is a special register having the address of an IO device that enables it to access the address taking it from DX register. So, the microprocessor gets the address from DX register, goes to that particular device to perform the required data transfer. Having just mentioned the operation of AX, AL, AH, DX, CX, CL and DX, you will be in a position now to understand the importance of these general purpose register, apart from trying to say that it has the required data. Now, we are looking into the next part, that is the arithmetic logic unit. This arithmetic logic unit is a 16 bit having both the operands being brought into arithmetic logic unit, and the result is stored back into the required registers or memory location. So, let us look into the different operations that is being done by this arithmetic logic unit. Arithmetic logic unit is a 16 bit wide. It can do the following operations on either from the memory location or from the registers: addition, subtraction, multiplication and division. So, the number that it can really work on is unsigned binary numbers, signed binary numbers which we call as an integers, unsigned packed decimal numbers, unsigned unpacked decimal numbers. Now, I will be talking about these different numbers as we go further into the subject, but for the time being let me inform you that unsigned binary number is a number where the MSB bit is not considered for sign. All the 8 bits or 16 bit number is a binary number. When you talk about signed binary number, the MSB bit is considered to be a sign number. If it is equal to 0, we call it as positive, where MSB bit is 1, we call it as negative. Unsigned packed decimal number. So, whenever we are trying to talk about the decimal number, we represent the number in binary coded decimal. When you say binary coded decimal, we require 4 bits to represent 0 to 9, and we use these numbers 0 to 9 starting from 0 as 0000, 9 as 1001, and these numbers can be packed in a register of 8 bits. That means that 2 digits can come into one particular register of 8 bits. When you are trying to talk about a 16 bit packed number, we try to say that we can have 4 digits in one particular register of 16 bits. Now, unsigned, because these numbers, since it's being 4 bits are being used to represent each digit, we cannot have a sign, hence it becomes an unsigned packed decimal number. When you say unsigned unpacked decimal number, it says that we are going to have the number which uses 8 bits to represent one digit. Say for example, if you want to represent 4, we put it as equal to 00001000. What does it mean? It means that we have the higher nibble to be equal to 0 and lower nibble will tell you the binary coded number. So, that means that a register of 8 bits can have only one digit. These are the numbers which you call it as unsigned unpacked decimal number. These are the 4 different type of numbers on which the microprocessor 8086 microprocessor works on. Now, let us look into the other operations that can be performed by the arithmetic logic unit. There are a lot of logical operations being done, such as NOT operation, AND operation, OR operation, XOR operation and test operation. Let me not go into the details of these instruction, how it works and things, because we have the old system available when we are trying to understand the instruction set of 8086 microprocessor. Now, let us look into the next part where we have the bus interface unit. The bus interface unit has got a set of registers called segment registers. So, the segment registers, we have a special feature of this, we will discuss this in greater detail today. They are code segment, data segment, extra segment, stack segment. There are 4 segment register and 1 instruction pointer. Now, these segment registers are being used to make the address that is to be generated by the microprocessor to 16 bits. So, the code segment is a special register which is used for accessing the code of a particular memory location where operation code are being stored. Data segment register is a segment register which points towards the data. Similarly, extra segment is used to point to the data, whereas stack segment is used to point towards the stack. Instruction pointer is a special type of register which points to the next instruction that is being fetched into the microprocessor. The detail of the instruction pointer operation would be that whenever there is a sequential operation, automatically the instruction pointer will be incremented. So, this instruction pointer increments by 1, 2 or 3 based on the type of the instruction that is being used. If it is a 1 byte instruction, the instruction pointer increments by 1 to fetch the next data. If the instruction pointer, this particular point would have been very clearly understood provided we have understood the complete instruction set. Since we are now interested in trying to talk about the architecture, invariably the instruction pointer always points to the even address and fetches 2 bytes and puts it into the queue. The operation of 8086 fetching 2 instructions and putting into the queue would be discussed in greater detail in the coming class. So, to summarize, let me briefly tell you that what has happened in today's class. We have been discussing about the different type of x86 processor which has been brought by Intel into the market, and we just mentioned that we started off 4004 processor which had a lot of applications too. To name one simple example of its application, 4004 was being used for the toothbrush to vibrate for kids to use for brushing. Then we got into 8008 8-bit processor. It was further improved to get 8080 microprocessor. 8080 microprocessor had some problems, so 8085 microprocessor was being brought. The difference between 8085 and 8080 microprocessor is that there are 2 instructions. The speed of operation of 8085 is better than 8080 microprocessor. The 2 instructions are sim and rim instruction. Following it, since these processors were only 8 bits and the external devices that were connected could access 8 bits and the speed was quite fast, the higher bit processors came into the market. The first one which came into the market is 8086. The 8086 microprocessor has had revolutionized the market, and Intel really worked with the Microsoft IBM to bring out. The Intel worked with IBM to bring out the first PC using 8088 microprocessor, and using this processor it was possible to bring out the first operating system called as CP/M system. Following it, we got 80286, and the IBM brought out another processor system to the market, which is IBM 80 system, which was very widely used. It had a lot of additional features of security which made it much more powerful. Since that was not enough, the speed of operation and the usage was not enough, it was further improved to bring out the higher bit of processors like 8080, 80386, 80486, Pentium, Itanium, etc. Then we have discussed briefly regarding the bus interface unit and execution unit. We looked into the different blocks what we have in each unit, execution unit having the AX register and arithmetic logic unit, flag register and also a control unit, the bus interface unit having the segment register, instruction pointer and the queue. We will discuss the remaining in the next class. Thank you.